Okay, so we want to explore exponential model of growth. And here's the first example. So let's read the problem carefully. A type of bacteria grows so that it triples in number every day. On the day that Roger begins observing the bacteria, the sample has a population of 100. So initially we're starting at 100. That's when we start observing it. After 4 days, okay, so here let's create a simple table. Okay, days and the actual population growth. So I'm just going to use n here for number of days. So initially it's 100. When it's 1, it's going to triple. So it's going to be 100 times by 3. The second day it's going to be 100 times by 3 squared, because you got to times that by 3 again, right? Next day you got to times this by 3 again, and I'm going to get that. And then I'm going to get that, okay? So on day 4, 1, 2, 3, 4, we're going to have this, which is 8100. Okay, so that's how we answer part A. And what's important, like I did this on purpose. I didn't evaluate, right? I just wrote the pattern out, because we're gonna need to use that to form an equation. Okay, so write an equation part B. Okay, so the population is going to be dependent on n. It's a function of n, where n is number of days. Initially we start with 100. Okay, and when n is 1, we get 3 to the power of 1. When n is 2, we get 3 to the power of 2. When n is 3, it's 3 to the power of 3, and so on. So this is going to be 3 to the power of n. Okay, that's what models this pattern here. In general, the population is a function of n. It's going to be the initial population. That represents initial population times by the exponential growth rates. In this case, they tell us it triples. So different question will tell you different things, right? To the power of n. Okay, so let's continue. See, graph the relation. Is this a function? Okay, so these are basically our points. When it's 0, it's 100. So let's go up by 100. And next it goes up. Next one is 300. When it's 0, it's 100. When it's 1, it's 300, and when it's 2, it's 900. So 1, 2, it's gonna be way up here somewhere. So the graph goes up like this. Okay, and it's actually gonna approach. If you extend it in the negative value, it's gonna approach that x-axis, or n-axis to be more precise. That's our graph. Right, you can see that's a function because it passes the vertical line test. Okay, assume this trend continues. Predict the population. 1 week, that's P at 7. 2 weeks, that's P at 14. Once you have the equation, right, you just have to replace the n with these values, and you'll get your answer. So it's 100 times by 3 to the power of 7. This is 100 times by 3 to the power of 14. Okay. So I'll leave up to you to punch down the calculator to evaluate those exact values. E. Describe the pattern of finite differences of this relationship. Finite differences are referring to the difference, right, for the y values, in this case the p values. Okay, so here the difference is 200. 900 to 300 is 600. Okay, and then we have 27 minus 9. Minus 9 will give you 1800. Okay, and that's 81 minus 27. Okay, that's the first finite difference. Okay, we're just taking the difference between the y's. Then it's 400. Okay, and then it's going to be 1200. Okay, and then it's going to be 3600. So if it's an exponential function, the second finite difference will increase by a constant multiple, like times by 3, times by 3. That's how we can verify that it's an exponential function. If it increases by the same common ratio, we call this a common ratio, right? So increases by 3 times, the next one also increases by 3 times, right? That's how we can verify through just looking at the numbers. If you didn't have the equation, that we can verify this is an exponential function.